So we're very lucky to have Mike here. He is the Deputy Director of Science at the British Antarctic Survey, or BAS. He also is a professor at the Scottish Association for Marine Science, or SAMS. And Mike, as if that wasn't enough, is also the leader of the Polar Oceans Research Group at BAS. We're really glad to have him here today. He's one of the founding members of SOOS, which stands for the Southern Ocean Observing System. And he's actually currently still the co-chair of SOOS. He is, no? He's nodding his head. So he was very recently the co-chair of SOOS. But Mike has his observational chops. He's done at least 16 research cruises in the Southern Ocean. And the one thing I will say about Mike on a personal note, we've heard about SOOS and SAMS and BAS. I know from personal experience he's a master crossword solver. And I think this helps with his acronyms and creative acronyms for his research projects. So go ahead, Mike.
Thank you very much, Andy. Yeah, I hadn't imagined being talking about crosswords to begin with, but there you go. It's a pleasure to be here and give this talk. This is a talk about Southern Ocean observations and what's going on and what isn't going on and why we might need it. It's a talk on behalf of a very large number of people, some of whom are here. But essentially it's a community that some years ago realized that sustained observations in the Southern Ocean were in a state that were not fit for purpose by any stretch of the imagination. And they needed to be more strategic, and they needed to be more sustained, and they needed to be put on a proper footing. And because of that, this group started something called the Southern Ocean Observing System. It's ongoing, and I'll tell you more about that, but really this talk is on behalf of everyone that's contributed to that. So I'm thankful to the organizers for inviting me here to give this talk, and this is specifically what they said when they invited me. They said, can you talk about the state of the Southern Ocean observations, and don't worry if it's controversial. And of course, to me, that's like that's the dream mission, is to offend as many people as possible. But then they did warn me that they're going to film the talks as well. So because I live in permanent fear of YouTube, I'm actually going to be incredibly uncontroversial. And I'm going to make essentially just these three key points. And I suspect that everyone in this room would happily subscribe to these, or at least I hope they would. The first point is that the Southern Ocean is globally important and is changing. The second point is that understanding these changes and their impacts is at present critically limited by lack of observations. And the third point is, of course, that we can, must, and will do better, but that it requires a lot more strategic planning and prioritization of the observations than has historically existed in the Southern Ocean. So the first point, Southern Ocean is globally important. I thought I'd start off by showing you this schematic, and this is something that SOOS put together when it was deciding where to put its efforts. And observing systems, we all know how useful they are, and we all know the value of sustained observations. But a key point is that if you're making these sustained observations, you really need to know why you're doing it, and you need to know how you're going to use the observations and who's going to use those observations and what you're going to get out of it. And this is a point that people like John Marshall make incredibly well, is that measurements are valuable, but you really need to know what you're going to do with them and why. So we went into quite a lot of detail on this, and this schematic summarizes what came out as the big drivers for making sustained observations in the Southern Ocean. Just to take you through them very quickly, one is that the Southern Ocean is very, very strongly connected with the rest of the world in terms of the exchanges of heat, freshwater nutrients, and so on. This is the thermohaline circulation of the global ocean that we're talking about here. Related to that is the overturning circulation in the Southern Ocean, which obviously reprocesses the water masses that enter the Southern Ocean and change them. Some become a lot denser and flow outwards. Some become less dense and flow outwards. But these are very, very important processes, and you'll hear far more about these from the talks following by Andy and Rick and others. And related to this, of course, is the role that the Southern Ocean has in affecting carbon fluxes between the ocean and the atmosphere, because this is the major location in the world where deep waters rise up to the surface and can then exchange their carbon load with the surface, draw down anthropogenic carbon and other carbon from the atmosphere, and take it into the interior of the ocean. The other reasons, the Southern Ocean is next to the world's biggest ice cap. The majority of the world's fresh water is stored on the Antarctic as glacial ice. but it's not immune from the ocean, and there's increasing evidence that the warming of the ocean, certainly in some sectors around the Antarctic, is acting to influence the ice shelves and destabilize the ice sheet. And obviously that has consequences for sea level rise. Related to all of these things is the sea ice, which is a key feature of the Southern Ocean. And it impacts all sorts of things like albedo and air-sea fluxes. And as well, it's obviously a unique ecological habitat. And related to that final point is the Southern Ocean is the site of some very important ecosystems. We think of them as being vulnerable to climatic change, and certainly some of them are. And you know, there are conservation issues just from that point alone. But you have to bear in mind that some of them are commercially exploited as well. And it's a little unfortunate this arrow ended up pointing at a penguin, because we're not advocating harvesting of penguins in any way. But there are species in the Southern Ocean, fish species, also krill, that are commercial species. And people's livelihoods depend on these. So they have to be exploited in a rational, sustained, manageable way. But the Southern Ocean is changing. All these things matter, and we know that they matter, but this is in a context where the Southern Ocean is changing. And in some cases, it's changing very dramatically. We can see the big warming signals, and see the big freshening signals. This is from a classic paper a few years ago. And these are big signals, and now we think of them as big, blurty signals that are impossible to miss. But it wasn't that long ago that we were all very surprised by these signals. And when the papers first appeared, they were revolutionary. So it's not that long ago that these changes first came to light and surprised everybody. There are other changes that are far more subtle. For example, the circumpolar current, the big current that flows clockwise around the Antarctic, it does change its transport, but it changes it in rather a limited way. And we have some understanding of why that is. You actually see far more changes in the intensity of the eddy field in the Southern Ocean, which is one of the reasons that the circumpolar transport is as constant as it is. And this is from a recent paper by Andy and colleagues, and he will go into far more detail, I think, in his talk. Other changes include, as I mentioned, the warming of the ocean around the Antarctic and the role it's having on the ice shelves and the ice sheet. So the background here is the temperature. This is the warm sector of Antarctica. This is the cold sector. And these red dots here, these are the regions where the ice shelves are melting and retreating very rapidly. And there's increasing evidence that this is driven by the warming of the ocean in these sectors. It's not necessarily just that the ocean's getting warmer, it's just that warm water can access the shelves more readily in some places. And of course, once you destabilize the ice shelves, the glacial ice can flow much more rapidly into the ocean. It's not a linear thing. Once these goes, you can get some changes that propagate for much longer and are much more significant than just the melting alone would indicate. And the changes are not limited just to the physical system. In some regions, there are known to be some very rapid changes in the ecosystem as well. What I've circled here is the Antarctic Peninsula, which is a nice case study because it's the region that's warming most rapidly of anywhere in the southern hemisphere. It's also a very well-studied region. And one of the things we know about the peninsula is that the ecosystem is indeed changing very rapidly. This is from the penguin populations that are monitored close to Palmer Station on the peninsula. You can see that some of the penguin species are doing very badly and other species are doing very much better as the climate is changing. I'm sure that Eileen Hoffman and colleagues from the ecosystem world will tell us far more about these sorts of changes during the course of the week. It's not just necessarily these very local scales that the ecosystem is changing. This is an example of a much larger regional changes that are ongoing. This is the work that Angus Atkinson did some years ago now about the change in krill populations in the Southern Ocean. And krill is one of the cornerstone species of the Southern Ocean food webs. And in the Atlantic sector of the Southern Ocean, the krill populations have declined in recent decades very, very dramatically. So hopefully you're convinced that the Southern Ocean matters and that we need to understand it. And that from the data that we have, we can say that there are some very pronounced changes ongoing in the Southern Ocean. These are changes that we need to know about. The second point I would make, and I have to apologize for the terrible pun, the changes we've observed or think we observed are really only the tip of the iceberg. We can only infer the changes from the data that we've got, and the data we've got is, unfortunately, woefully inadequate. The reason being, the Southern Ocean has historically been one of the world's biggest data deserts. And the point there is that the data that we've got have come from actually a very limited number of sources. There are ship-based measurements, which are, of course, invaluable, but very few ships go to the Southern Ocean. It's not a big trade route. Hardly any ships at all in winter go to the Southern Ocean. Invaluable data, but very sparse. There are shore-based measurements of the ocean, but Antarctica is, of course, the least inhabited continent. So although it's got a big coastline, there's very few observations made from land. Instruments are deployed from the ships that go to the Southern Ocean, such as floats and moorings. And again, all of these data sources are absolutely invaluable. But the Southern Ocean is a very harsh place. It's a very rough, wild environment. And of course, the sea ice makes it incredibly difficult to get data from things like floats. So a lot of these instruments have to be developed very carefully, and you do accept when you deploy them, there's a high chance that you won't get them back again. And of course, satellites, but they can't do everything. Incredibly useful, but they can't do everything. So the existing observing system elements, this is kind of a subset of what we have at the moment. There is far more, but this is kind of the backbone of some of the elements of the observing system. This is the repeat hydrography sections. This is something that Andy alluded to. This started with WOST, the World Ocean Circulation Experiment. These are the big long lines done by ship with high quality data and carbon measurements and tracer measurements. And the coverage doesn't look bad, but you've got to bear in mind, this is done once every 10 years, something like that. These sections are repeated. But some of them are repeated annually, Drake Passage, south of Australia. But in practice, most of these lines happen once every 10 years. There's ships of opportunity, XPT sections, plankton recorder, moorings. There is a mooring network around the Antarctic. It's relatively sparse, but it's better than having nothing. This is, of course, the telling plot. This is the Argo coverage in the Southern Ocean. These red squares show where there's been no Argo measurements made. So as you pull in towards the continent itself, the coverage decreases very rapidly. So there are things there to give us data, but it's not enough. And I was going to give you just a little case study of what you can and what you can't do with the current observing system that we have. And this is the sobering example. Every year there's an article in BAMS called State of the Climate, and it's a report for the previous year in terms of what is the climate, what does it look like, what do we think is going on. And this year they asked for a section on the Southern Ocean, which is great. So the question was, what could be assessed for 2014? And the things that could be assessed were things that you can get from satellite, like temperature, things about the circulation, if not the circulation itself, sea ice, all good. Things about the upper ocean that you get from Argo, so heat content, mixed layer depth, some things about water mass changes. A few scraps of things about the shelf regions from some of the programs on the shelves around the Antarctic. A few scraps about carbon, mainly from underway sampling. That was kind of it. That's really all you could be said at the moment about what the Southern Ocean looked like in 2014. What could not be assessed? Deep ocean water masses, aside from a few sparse pieces of repeat hydrography. Biogeochemistry across very large areas of the Southern Ocean. This is changing. I'll say something about that in a moment. But for 2014, there was very little could be said. Apart from a few bits in the Weddell Sea, nothing at all about what's happening underneath the sea ice. Nothing at all about what's happening underneath the ice shelves in Antarctica. And apart from some specific sites, such as South Georgia and the peninsula and other places, the biological variables across huge parts of the Southern Ocean, completely unknown for 2014. And for me, as an observational scientist, this is all great, and we can do some wonderful things, but this is, it needs attention. It's not good enough. And again, these are just indicators, really, of where we're doing well and where we're not. This is Argo again. I showed the points there. This is all the Argo trajectories from the Southern Ocean. And you can see around the ACC region, it's pretty good, a lot of data. But once you get into the ice-covered regions, here in the Ross Sea, here in the Weddell Sea, the coverage drops very dramatically. And the fact there's any data at all from the Weddell Sea is largely thanks to people like the Alfred Wegener Institute, who maintain the sound source network in the Weddell Sea so they can track floats beneath the sea ice. Oceansides track the mooring network in the world. This is the status at the end of last year. Obviously, the equatorial regions are moorings heaven. If you're a mooring scientist, I strongly advise you to go and do your science there. The North Atlantic isn't too bad. The Weddell Sea isn't too bad, to be honest. Again, largely this is because of people like the Alfred Wegener Institute. This is a little cluster of bass moorings here. But across huge parts of the Southern Ocean, there's nothing. And VOS is the voluntary observing ships. It's the observing network from things like container ships and passenger vessels and what have you. And because there's no trade routes in the Southern Ocean, again, you get very, very little at all. So when you collate this picture of gloom, this is kind of what you get. And we came up with a schematic. And essentially what we did was to structure the Southern Ocean into 5 different sampling regimes. So number 1 was the upper ocean of the open ocean above 2,000 meters. And 2,000 meters is the standard Argo depth, which is why we did that. Number 2 is the deep ocean below that depth. Number 3 is kind of the open shelf region and the slope around Antarctica. Number 4 is the ocean beneath the floating part of the Antarctic ice sheet, the ice shelves. And number 5 is the very surface of the ocean. And the point really here is that only part of the first sector is anywhere near sufficiently sampled. And when I say part of it, I mean the part that's north of the seasonal sea ice zone. So it's this half of box 1. And that's because of Argo. Everywhere else, there's a real critical shortage of observations. When I say it's sampled well enough, at present, that's only really for physics, because Argo has really only made physical measurements in large part up until the present, though that is changing. The key point, more sustained observations are needed, but we have limited resource. So to maximize their usefulness, and therefore to maximize the sustainability of the observing system, they need to be strategic, they need to be properly coordinated, so that you get the right data in the right place at the right time, and in a useful way, so you can actually map the data onto the big scientific and societal issues. So we need to do better, and the question is, what does better look like, and how do we do better? So in that context, the key point, things are changing, and that's good news. But things are changing in a way that we need to be alert to. This is a research ship. I'm sure you realize that. It's a very nice one. I've spent a long time on it. It's the James Clark Ross. The number of research ships in the world is unlikely to increase significantly in the near future. They're very expensive. Some nations are cutting back on their research fleets. Other nations are building 1 or 2 more ships. But the total number of research ships capable of working in the Southern Ocean is probably close to the maximum we're going to see in the next few decades. And that limits what you can do. Ships can only be in one place at one time. There's a constraint right there. Conversely, the number of these autonomous vehicles, this is a SOCOM glider, is rising rapidly, and that is set to continue. These are, in many respects, the future. These are sorts of autonomous vehicles of ocean observing systems. The number of these hardworking, underpaid research scientists, I wouldn't even like to speculate on. In the UK, maybe not too good at the moment, but elsewhere, I hope is doing better. So I mentioned autonomous vehicles. They are, I believe, the future of these sorts of observing systems. And what we really need is swarms of them in ever greater densities to give us the spatial coverage and the temporal coverage to map and monitor all these things that we really want. And when they were developed, like Argo, they started off being primarily physical tools, measuring the temperature and the salinity of the ocean. But progressively, we're getting more and more sophisticated with what can be done. This is a glider with a micro-rider. This is a turbulence probe. This is technology that Andy Thompson, amongst others, has used. These are the echo sounders that give you krill density measurements. So we're getting biological variables from these autonomous platforms as well. They need to be paired. These are underwater gliders. They need to be paired with surface vehicles. This is one of the wave gliders that can power themselves from waves and solar panels. And these are absolutely vital, especially in the Southern Ocean, because they stay at the surface. And they can be instrumented to give air-sea flux measurements of things like heat, momentum, carbon, and so on. And this is one of the big areas where measurements are very, very critically needed. There's other technology out there that can really help with development of these observing systems as well. This is to do with the tagging effort on marine mammals. You can see here, this is one of the tags. This is actually a mini CTD that is glued to the head of this mammal. It's a very humane thing, and the biologists love this data, and they get sort of interdisciplinary measurements that help them with their science. But they transmit their data via satellite, and some of these species can dive very deep. And it's incredibly valuable data. So this is the profiles that you get from the seal tagging work in the Southern Ocean. Most of this is from elephant seals, which can swim for thousands of miles and dive down to 1,500 meters or deeper. And you get more than 2 profiles a day from elephant seals when they're tagged. It's incredibly dense data. It's not as high quality as Argo or certainly ship CTDs, but it's of a comparable quality to ex-CTD data. And by tagging different species, this is a Weddell seal here, by tagging different species, you can actually target measurements at areas that are otherwise very difficult to get to. And the nice thing about Weddell seals is they live south, very close to the Antarctic, even in winter. They have a very unique life history from that point of view. By tagging Weddell seals, you can get data from areas where certainly ships can't go in winter. Argo floats were likely to be damaged and destroyed. There's very, very few ways of getting this sort of data, but it is possible. And the point I wanted to make here, of course, is this needs to be sustained systematically. And I'm giving the UK example here. The UK is where these tags are built, but they're not in anybody's sustained observational program in the UK. So the UK only makes these measurements when someone gets a grant funded. And to my mind, that is virtually criminal, and yet is where we are. Other ways forward. What I've written here is enhancements to conventional Argo, and I put conventional in quotes because it wasn't that long ago that Argo was new and sexy and cutting edge and was going to change science, and it has done. But people want more. We've seen the reasons why we need more. And these are sorts of enhancements that we're seeing coming through now. Deep Argo. Conventional Argo is limited to 2,000 meters. The deep ocean, certainly the deep Southern Ocean, very critically important. Deep Argo is coming through and offers very great potential to get into that deep water on a much more high-resolution basis than has been possible before. I would argue, of course, that it needs to be ice-capable floats, not just standard floats, because the ice-covered regions are very important in terms of the deep ocean. And biogeochemical sensors on the float arrays is a program starting now. I'm sure we'll hear more about this week. Called SOCOM, and it's to do exactly that in the Southern Ocean. I wrote courtesy Ken Johnson here. I just stole this off his webpage, so he didn't know about that. But you can get all these different parameters measured now on Argo floats, including carbon system measurements, and this is incredibly important. This has a finite lifetime, but hopefully the case that will come through from the science that will happen will persuade people that these are the measurements that need to be made on a sustained basis into the foreseeable future. And I mentioned the sound sources in the Weddell Sea that's used for tracking Argo floats. Obviously, we need them in places like the Ross Sea and the other ice-covered areas of the Southern Ocean. And we need to transfer that capability, not just have them on passive floats, but have them on gliders so that we can have gliders in the Southern Ocean in winter, control them, get data from them. That technology, people have done this in the Arctic. That technology is, if not mature, it's certainly on the verge of being mature. We need to roll it out in the Southern Ocean. It's expensive, but the data is very, very valuable. And certainly we need more of the measurements underneath the ice shelves. And these are the floating parts of the Antarctic ice sheets. And these are the critical places that control what the ocean does to the Antarctic ice cap and what that ice cap does to the ocean. And it's also the hardest place in the ocean to get measurements. But we can do it. There's different technologies that allow us to do that. One is hot water drilling, where essentially you bore a hole through however many 100 meters of ice shelf you're in, and you can deploy instruments through that. You can deploy moorings through that. You can leave the cable in and get the data back via satellite. It's expensive. The data are always spatially sparse, but it's incredibly important. They need to be turbulence resolving measurements. The other standard way of getting measurements from underneath these ice shelves is via autonomous technologies. This is AutoSub. This is the UK's unmanned submersible for science. There's been a number of missions now with AutoSub underneath ice shelves. Again, it's expensive. Logistically, it's very challenging. But the data really do give you these new insights into how these systems work. And we need far more of them. We need to develop this technology from its current state. We need long-duration AUVs. And the plan here is to have AUVs that can virtually live underneath ice shelves. And they can sit on the seafloor and hibernate for long periods, then come alive, make some measurements, talk to hydrophones deployed through holes through the ice shelf, upload their data, and go back to sleep again. These are the sorts of things we need to develop for the future. So technology developments offer the potential for the data required, but obviously it takes a lot of time to get them in place. It takes money, which has to be gone and won from somebody. What are the immediate priorities? I don't intend to read these out for you, but at the moment they relate to things like filling important geographical gaps, developing year-round data coverage, so wintertime measurements, expanding the range of parameters being measured, especially for things like the carbon system. And in some cases, particularly in regard to the biological systems, actually deciding what it is that needs to be measured on a sustained basis and what you can actually live without, given that you can't measure everything. And there's people like Andrew Constable who are putting a lot of effort into actually determining these things. So that's the short term. In the longer term, and we sort of put a kind of a 20-year vision on this. What do we envisage this observing system looking like? And essentially, it comes back to all the autonomous things that we've just been talking about. The vision is for something that relies very heavily on cyber infrastructure-based systems. And the idea here is that if you have, for example, a swarm of gliders, if you have 10 gliders, you can have a small number of pilots controlling them in real time. That's not difficult. If you had 100 gliders or 500 gliders, it becomes very much harder to actually do that work. So what you really need to do is have these gliders work together in intelligent ways. So you set overall mission parameters for them, and then the gliders talk to each other, but also talk via satellite to land stations, and kind of map out their mission in an ongoing way and change where they go and when they go there on the basis of optimally meeting those mission requirements. And the way we thought that would work, potentially best of all, is if the glider data and all the other data that's been collected were assimilated in real time into models, and then those model output fields were fed back to the gliders so they could update their mission parameters in real time without requiring human intervention. It sounds like science fiction. Possibly it is in some respects, but this is the sort of technology and the sort of thing you can do on that 20-year timescale if the investment comes through and if we're strategic about how we develop these things. I've talked about gliders a lot. There's other AUVs out there that would obviously work in the same way. You can only include variables that you can measure autonomously, but of course on a 20-year timescale, we'll be able to measure more and more and more things autonomously, and these will be rolled out as the technology becomes available. Is it sustainable? Possibly yes, possibly no. The idea, though, is that to actually keep these things in place, to build them and keep them in place for the sustainable future, you need to know who's going to use them, and you need to know who's going to pay for them. And again, that's not easy. People that would want a Southern Ocean observing system, obviously ourselves, but we don't have a lot of money. But there are a lot of other people as well. Resource managers, these are the people that oversee the Southern Ocean ecosystem exploitation, the sustainable harvesting of things like krill. Policymakers, Antarctic tourism operators. Antarctic tourism is on the increase, typically using ships with mixed results at times. Weather and climate forecasters, and so on. The question is, who of these has the most money? We know who of these has the most money. But unlike other oceans, we're limited in what we can do with industry because of the Antarctic Treaty. There's no hydrocarbon exploration allowed south of 60 South. So there is some activity going on north of 60 South, but it's not as easy for us as it is for other ocean observing systems. So in this context, what I thought would do is just show you this diagram. This is from a paper that came out very recently in nature climate change. What it shows is a feedback loop in the design and the implementation of ocean observing systems. And the idea here is that if you get this feedback loop working correctly, it can give you a sustainable observing system. And the idea for this feedback loop was you start off with the scientific and societal issues, and those control what you measure. And that controls what platforms you need, and that dictates what knowledge you get, what data products you can build, what data streams you can enable. And if you get those right, then you can actually make a difference to these issues and progress things, and the loop continues. And I believe that, and I think that's true, but at the same time, I think this diagram doesn't capture one of the most important things, which is that the people that own these issues, apart from the scientists, the industry, policymakers, they don't sit down and say, let's go and measure temperature. What they say is, we need information on climate in the next 20 years, or we need knowledge of what the climate system looks like now. So they push resource this way. They pay for knowledge. They pay for data products. They push the resource this way. Most of all, what they want is forecasts. So they will pay for forecasts by pushing money this way. And of course, once the money ends up here and people say there's money to be had in data products, that controls what measurements you make and what platforms you need. So this feedback loop has to work, but it's very much written or drawn here from the scientist's point of view. There's another feedback loop that more or less works the other way around, and that's from the people who own these issues. And those owners of these issues aren't the scientists. And to be honest, what it comes down to is there's a difference between useful, which is what we think our science and our observations should be, and usable and used. Because ultimately, if the products of what we produce aren't used by the people who own these issues, then there's no sustainability of the system. It's work in progress. People are hard at work some of the time. The end goal is something that is sustained and coherent and multidisciplinary and fit for purpose, and that will, in any given year, tell us what we need to know about the Southern Ocean, but can be adapted as new scientific and societal drivers come along. It can't be static. It's work in progress, but it's always going to be work in progress. It needs to be adaptable, both in terms of driving new technology developments and adopting them as they come along. It requires far greater international coordination than has currently existed, but it can be achieved. We know from examples like Argo that you can have successful international coordination of data collection on these spatial scales. The question is, are we going to do that with glider swarms? More and more nations are buying into this glider technology. Are we going to have coordinated international glider missions, as well as focused process studies? Are we going to have sustained observations with gliders coordinated internationally? And of course, it requires working across traditional disciplinary boundaries, and we always pay lip service to this. But in practice, because of the way these things are going to play out in the future, there'll be a limited number of assets, and we have to get the maximum amount of data off them to benefit all of these issues. Status, embryonic but growing. Some of the elements are mature, others are still being developed. Some of them are still more or less at the concept stage in terms of specifying what's needed, but that's being worked on. Assessments are being carried out to define things like the spatial and temporal sampling requirements and the gaps. The implementation will inevitably be regional in a lot of cases, because there are already groups that work on those levels that naturally form themselves together into cohorts. But also you've got to bear in mind that some of these things can only be funded regionally because each individual nation will only have limited resource that it can deploy. A data system is being built, data product system is being built. The cyber infrastructure is in a lot of people's minds, and Andy and others have actually started work on how you take this forward and how you build these things. It's very important, and I do see it being critical in the future. So I'm all finished now. This is the last slide. Just a final word. I thought I'd leave you with two quotes. The first one, many more voyages of discovery are also needed, especially in the vast expanses of the southern seas that remain relatively unexplored. The reason I like this quote is that it's not from a scientific journal, it's actually from The Economist magazine. It's an article that they wrote called Troubled Waters in 2009, and it actually puts numbers on the financial value of the global oceans. It's fascinating if you've never read it. The things I particularly like it, of course, is because 2009 was when the global economy was tanking and no one had any money. And yet the economists were still advocating sustained observations or exploration of the Southern Ocean. And you can question how clever these economists are, because they didn't see the global economy was going to tank. But in this particular aspect, certainly I think I choose to believe what they're saying. But here's another quote. The real voyage of discovery consists not in seeking new landscape, but in having new eyes. And in this context, the new eyes is the technology that is now coming through that will enable us to see the Southern Ocean in new ways into the future. I'll stop there. Thank you very much.